Yo, Mr. Martin back at it again with a brand new video. This is 6.2. We're going to talk about recursive formulas. This is where we actually put down the math. Okay, we're going to talk about how to identify special patterns in a sequence, and then we're going to actually write some formulas. This is going to look super mathy to some of you, but at the end of the day, you're going to feel really good about how this looks. Okay, so let's jump right into it. We got a little bit of vocab. This is a recursive formula, and what this means is that it relates to a term in the sequence to the preceding term. Okay, and remember that word preceding means the previous term or the term before. Okay, preceding something before. And then another part, when we write our recursive formulas, this is a requirement right here. You must denote the first term in your formula. Okay, this is highly critical, and that word denote means we just need to write it down. We need to list it. Okay, so when we write this recursive formula, do not forget that first term. All right, so let's learn how to write a recursive formula. In order to do that, we need a sequence to use. This is the one that we're going to use right here. Okay, so we got 40, 35, 30, 25. Oh, forgot my dot again. Oops. Dot. There we go. So take a look, try and figure out how are we going from one term to the next. I'm going to draw these little arrows while you're thinking about it yourself. You've probably already figured it out right now. And that is we are subtracting 5 from one term to the next. Okay, not too bad. It looks like it goes. The sequence or the pattern follows the sequence. We are good. So 25 minus 5, that next number in the sequence is going to be 20. Okay, and then it wants us to justify our reasoning. So we want to write this out in complete sentences. All right, bam, look at that, like magic. From one term to the next, 5 was subtracted. So somewhere along those lines, you could write something out to justify your reasoning. All right, now let's move on over to this table that we got on the right. Remember, we said that n, that variable n, is our unknown term. Okay, and then a of n, remember this is that function notation right here. This is saying that this is what our term number is equal to. So our first term is equal to 40. We go down this list, it looks like what we had here on the left. We know that our next term is 20. Okay, so what I want you guys to think about, I'm going to draw these little arrows just so we know which way in the table we're going. We're going top to bottom right here. So we said when we went from 40 to 35, we took away 5, right? From 35 to 30, okay, we took away 5. All right, we're going to repeat this pattern going down. All right, there you have it. Okay, so we said one term to the next, we went minus 5. Okay, so if we go back to our definition, I'm going to flip back to that page. Remember, we were talking about something with the preceding term. So we want to think of the term that is going back. So from this part of the table, I am going to go backwards. Okay, remember, I'm thinking about the previous term. So if I'm at my 5th term, okay, I'm going to write down this 5 right here. If I'm starting at my 5th term and I'm thinking about the preceding term, okay, what operation can I do here to get from 5 to 4? Well, I can subtract 1. So if I'm thinking about finding the term that came before 5, I would just think one term back. So, 5 minus 1. Okay, and it's the same thing if I'm starting at 4 and I want to find the previous term. I would do 4 minus 1. Okay, so let me fill out the rest of this table for you. All right, good. How you like that? Okay, so if we are at term 2, we're looking for the preceding term. We're doing 2 minus 1. Okay, if you think back to 6.1 when we originally introduced sequences, we said that the letter n was our unknown term, right? So if I am at my nth term, remember n could be, right now it looks like it's the 6th term, but it could be the 50th term, could be the 130th term, could be the 1000th term. Okay, but we call this the nth term because we don't know what term we're talking about. We're just talking about any term. So if I am at my nth term and I want to go back to the term before my nth term, take a look at what we did here. How did we go back to the previous one? We subtracted 1. So if I'm at my nth term and I want to go back, it's simply just n minus 1. Okay, so this is a little piece of that information that we need. And then now we're going to break this into how does this equal out to our function. Remember, we said the first term equals our a of n as in 40. So if I have in function notation, right, if I say the function of my previous term, okay, a of the previous term, how do I get to my next term? Well, from here to my next term, we did -5, so that's what we're going to do right here. So if I think back to my previous term to get to the next one, I am subtracting 5. All right, now this is how we write that recursive formula. I'm going to write this in that function notation that we're using right here. So I'm going to say a of n, right? This is a of n. I'm looking for what my term is going to equal to. A of n is equal to taking my previous term, a of n minus 1, and then I'm subtracting 5 from it. But don't forget, we must denote that first term. So I'm going to do that here by adding this semicolon, and then I'm going to say a of 1 for my first term is equal to, bam, 40 right there. That is my first term. Okay, remember, we can do this in subscript also, and it's just going to look something like this. Okay, so that n minus 1 is that subscript down below. Then I go back above and I write that -5, put that semicolon, and then I say a sub 1, my first term, is equal to 40. Alright, so make sure you practice this. All it takes is doing, I don't know, maybe like 3, 4, 5 of these guys right here, and then you're going to be good to go. Alright, let's take a look at the next example. Example number 2. We got this sequence here, 2, 8, 32, 128. Take a minute right there and think about how we're getting from one term to the next. Boom, you probably already got it. It looks like we are multiplying by 4. So I'm going to say times 4 times 4 times 4. And then how do we figure out the next term? Well, 128 times 4. Okay, we type that in our calculator, or we use the power of positive thinking. We're going to get 512. Now we want to write a recursive formula. Down here it looks like we used a sequence name of G, and it looks like we're writing in subscript. So let's go ahead and do that in subscript. We're always going to start off with saying, hey, G of n, that output is equal to, right, my previous term of G sub n minus 1. And then what did I do to get to the next term? Well, I multiplied by 4. I'm going to use the dot instead of that little x right there. G sub n minus 1 times 4. Then I'm going to put that semicolon, and then I'm going to say G sub 1 is equal to my first term, 2. Very good. So let's go ahead and graph this, right? We said our first term is 2, so probably like way down there. Second term is 8, a little bit closer to 10. Third term is 32. Looks like we got to jump up a little bit. Fourth term, bam, all the way up here, 128, real close to 130. This looks like it's rolling out slow and then skyrockets up. All right, you want to hear that again? So what kind of graph does this form? Remember, when it's got that drastic change, we are talking about an exponential. Okay, so this is a exponential graph. Alright, let's take a look here. We got another little bit of vocab. So we got what we call an arithmetic sequence. Okay, this is where each term is the result of adding a previous term and a real number, and this is what's going to form a linear relationship. Okay, so I want to give you this example here. I want you guys to write this down. We're going to take a look at this little sequence right here. We got 10, 8, 6, and 4. Okay, and we're asking how do we get from one term to the next? Well, we're simply subtracting 2. Okay, so if we're subtracting 2, are we going to be that arithmetic sequence? Here it says we need to add from the previous term, and here we're subtracting. You know, don't let that fool you. Okay, this is still an arithmetic sequence because subtracting 2, right, this is exactly the same as adding a -2. There's not much different to it. All we're doing is saying plus -2, because remember, positive times a negative is a negative. This is the same as -2. So let's go ahead and write this arithmetic sequence. I'm just going to use a sub n is equal to a sub n minus 1. Okay, and then what am I doing? I'm doing minus 2. I got my semicolon, a sub 1. This is equal to my first term, which is 10. See, that's not so bad. Pretty easy to remember. All right, let's think about the shape of this graph. Well, looks like we're going down. We said it was a linear relationship on a graph. It should look something like this. So we end up having a constant difference between these values. It is constant all the way down. So constant difference. Alright, not too bad. Okay, our next one that we got to think about, this is called a geometric sequence. And here we're going to multiply from the previous term. This is going to form that exponential again. I'm going to give you an example right here. Let me write these terms down. I got 48. I got 12. My next one, 3. Yup, you guessed it. We are dividing by 4 from one term to the next. Okay. So is this going to be a geometric? Well, the last one ended up being, even though it seemed kind of tricky, same thing here. Yes, it is, because dividing by 4 is the same as multiplying by its reciprocal, 1 over 4. Okay, remember, if we're dividing by 4, that's the same as multiplying by 1/4. Okay, so we're going to write our recursive formula. A sub n is equal to a sub n minus 1, and we are actually multiplying by 1/4. And then I got my semicolon, a sub 1, my first term. I'm starting off with 48. Alright, let's draw this on this graph. Okay, it looks like we started up high, and then we started dropping really big, and then just a little bit drop, and then a little bit drop. So we're kind of just swooping down. This is still an exponential, but we do have this drastic difference. Okay, so when it's drastic like that, boom, exponential. It's going to be geometric. Alright, we do have this one, not really a special case, but I kind of think of it as a special case. That's what helps me remember it, so maybe it'll help you remember it. But we got what we call a quadratic sequence. And this is just where we have some where we got the a common second difference. This is going to form what looks like a quadratic. So in order for us to see this, we need an example. We need a sequence here. I'm going to give you 3, 5, 8, and 12. Okay, if you haven't guessed already, from 3 to 5, looks like I'm adding 2, then it looks like I'm adding 3, then I'm adding 4, and so on. There should probably be some ... Okay. How would I write this? Okay, this one, we always start off the same, a sub n, then we look at, find that previous term, n minus 1, but with this common second difference, what we're doing right here, because we can't say plus 2 and then plus 3, we got this little trick in here that says we're going to say plus n. Okay, and this lets us know, boom, after we denote that first term, that we are increasing when we add up in this relationship here. So this is going to be a sub 1 is equal to 3. Alright, so make sure you remember those. Good way to do that is to make some flashcards, kind of quiz yourself, and see if you can commit these to memory. Alright, so we got 2 more examples here. Let's go through these. What does it look like we're doing? Looks like I am adding 11, adding 11, and adding 11. Alright, what are my next 3 terms? 49 plus 11, that's going to give me 60, then 71, and then 82. Okay, I'm going to start with a, let's do function notation. A of n is equal to a of n minus 1, and then plus 11. Let's put that semicolon, and then a of 1 is equal to my first term, 16. Boom. Alright, and then it asks us, is this geometric or arithmetic, and why? And then it wants us to describe what the graph will look like using complete sentences. Go ahead and pause the video here, write this down, see if you can get this, and then unpause the video and see what I put down. Alright, great job. So welcome back. So I said this is arithmetic. Remember, because we have a constant difference, we are adding 11 each time from one term to the next, and the graph's going to make a linear shape going upwards. We got that straight line. All right, and then my last example here. Okay, change this. This should have been n, and this should have been big B of n. Okay, so remember, anytime that you're given a graph, you kind of want to look at your axes. How are these labeled? If we look left to right, okay, my line's going down. I'm moving by units of 1. If I look going upwards, yes, they are numbered by 4s, but we do have these halfway marks. So this looks like we're going up by intervals of 2. So if my first dot is right here between 0 and 2, that means my first term is probably 1. My second term looks like it's going to be 9. My third term looks like it's going to be 19. And then my next term, fourth term, looks like 28. So let's try and think. We're probably not multiplying by 9, because 9 times 9 again would definitely not be 18. If we are adding, that would be our next guess. So adding by 8, but then 9 to 19 is going to be plus 10. Maybe we're adding by increases of 2. Oh, well, 19 to 28 is plus 9. This thing is kind of all over the place. So is it going to be arithmetic or geometric? Well, we don't really have a consistent pattern moving throughout the sequence, and that is okay. Sometimes it simply is not a sequence. So this is going to be neither. Okay, and then if we have neither, we just can't really write a recursive formula for this sequence. So I'm just going to put NA. All right, and then last but not least, okay, I want you at the bottom of your notes, you got a little bit of space there. There is some that I want you to write down, okay? Let's do this here. So maybe write some extra notes. Boom, just like that. Underline it, make it look good. All right, I'm going to give you this other example right here. Okay, so if we got 1, 2, 6, and 24, well, if I add by 1, okay, that's okay. Then maybe add by 4, so maybe I'm increasing by 3, so the next one would be by 7. Nope, doesn't work like that. What about multiplying? 1 to 2 would be multiplied by 2. 2 to 6 would be multiplied by 3. 6 to 24 multiplied by 4. Oh, looks like I got a cool little pattern going right there. Okay, so maybe this is something. All right. If I'm going to write the recursive formula for this, okay, this kind of is another little special case. I say that just because the way that we write these looks a little bit different. But I would write this a sub n is equal to a sub n minus 1. Remember, this part is always the same. But like the other one that increased as we went up in our pattern, okay, this is doing the same thing. But here we are multiplying. The other one we were adding in that quadratic. This one we are actually going to be multiplying by n. Okay, and if we take a look at the graph, if we were to actually graph this, it would kind of roll out slow, and then it's going to have this giant jump. So this is going to be an exponential, okay, and we can call this a geometric because it will have that drastic difference. Okay, so there really are 4 different types. We're either going to see something plus or minus the same number all the way throughout. We might see times the same number all the way throughout. Then we might see that plus n, or we might see that times n. So make sure you get a handle on each one of these types. Do that practice. Remember, if you need some help, reach out, talk to some of your buddies from school, ask a parent, ask a friend, reach out to your teacher. You always got tutor.com/military. There's tons of great, plentiful resources for you. Make sure you are using them. I had a blast. I hope you did too. I will catch you on the next video. You enjoy. Have a wonderful time. Peace out.